Okay, let me now give you a picture of gas injection, a physical picture of gas injection through a schematic of an axisymmetric injection. So, I have placed the nozzle at the central line, and this is the plume boundary, and this is the axis, and this represents the wall of the ladle. The nozzle is placed at the central line along the axis of symmetry. That is why it is an axisymmetric gas injection. So, we are injecting argon through the nozzle. Now, I have also mentioned to you that the injected flow rate of argon through the central nozzle varies over a wide range, and it is substantially smaller than the flow rates of oxygen that we use for steel making or primary steel making processes. And I have given you a value of about 0.1 to 1 normal meter cube per hour per plug. So, that is the kind of this is normal meter cube per minute per plug. That is the range of flow rate which one uses. This is the least flow rate, and this is the maximum flow rate. Now, under the ladle metallurgy gas injection operation, when we inject argon gas through a nozzle, for example, typically a big gas envelope forms in the vicinity of the nozzle. Now, this gas envelope it is typically hydrodynamically unstable. The fluid cannot really sustain that big a gas envelope. So, immediately above the gas injection nozzle, this big gas envelope typically devolves into a spectra of spherical cap bubbles, and these bubbles basically then rise due to their buoyancy and then escapes to the surrounding. So, the two-phase mixture that we see at the center, so we have some liquid steel here and dispersed bubbles here, this is typically called as a plume. So, the injected gas, given its buoyancy, rises to the free surface, and as a result of which it induces a turbulent recirculatory motion of liquid steel in the system. And it is well known that this moving molten steel, it helps in homogenization of the bath in terms of its chemical composition, in terms of its temperature, it aids in inclusion agglomeration, and also depending on the position of the nozzle, whether it is too closely located to the wall or not, it can also create some preferential refractory wear, particularly in the vicinity of the rising plume. In this case, of course, it is not significant because it is going to be equidistant from both the walls. Now, if we further look at the ladle and the two-phase region, it is basically divided into four different regions, and out of these four different regions, it is region 1 typically is called the momentum region. So, here the momentum of the gas is substantially larger, and so it is this particular region I am talking about, the momentum region. Immediately above this is a small little region, and this is also known as the transition region, and the largest region, of course, may be somewhere up to this. We can say that this is the region 3, and this region 3 is the buoyancy region. And finally, we have region 4, which is the surface or free surface region. So, this is the way a typical gas stirred the plume developed in a gas stirred liquid system, gas stirred ladle is going to develop. Momentum region and transition region and surface region, all these three combines will barely take about 20 to 30% of the entire height of the reactor. On the other hand, this region, the region 3, which is the buoyancy region, where we see nicely dispersed spherical cap bubbles, spherical cap because the thermophysical properties of water provides us that kind of region where only spherical cap shaped bubbles are possible. tiny, very small spherical cap bubbles or ellipsoidal bubbles are not possible there, because we have the standard chart or nomograms available, which gives us the shape of bubbles which are possible in various liquid systems in terms of Etoile number, Reynolds number, and so on. So, these spherical cap bubbles which we see within the core of the liquid, and the equilibriums their size are more or less governed by the thermophysical properties. We of course have here a spectra of bubble. There is coalescence and disintegration of the bubble, and a dynamic size range develops within this system, and the mean size range here is governed basically by the thermophysical properties of the fluid gas liquid system. It has very little, the nozzle or the orifice has very little role as far as the dynamics of this particular region is concerned, and that is why in ladle metallurgy steel making situation we often say that the gas injection through, or the nozzle dimensions, I would better say that the nozzle dimensions are not critical to the characteristics of the plume and the bulk recirculation which is produced. So, therefore, under ladle metallurgy gas injection operation, we can say that whether we inject gases through a porous plug, whether we inject gas through a nozzle or a submerged weir, the flow recirculation producers are not going to be critical to the very nature of the gas injection devices. So, in this particular region, region 1 and 2, of course, we may see some noticeable difference depending on the gas injection device, but by and large the plume region or the buoyancy region will be virtually unaffected by the details of the nozzle, gas injection nozzle, and so also the flow region. Now, the system typically is driven by potential energy and not kinetic energy, as we would normally anticipate. So, it is a potential energy driven system. The kinetic energy of the injected gas, and I would say that the kinetic energy of the injected gas, I can say half m dot u0 square, in which m dot represents the mass flow rate and u0 represents the velocity or free stream velocity through the orifice itself. And this quantity, which is the kinetic energy of the injected gas, is extremely small. How small? In comparison to the potential energy, the kinetic energy is hardly 1 to 2%. So, that is why we can consider that it is, that is why we say that it is a buoyancy driven flow in gas stirred ladle system and not a kinetic energy. For example, an oxygen steel making converter, OBM, where we have bottom blown oxygen steel making, where oxygen is going to be introduced through a bottom to air, that system is certainly not potential energy driven. There the kinetic energy of the injected gas plays a important role as far as the extent of flow recirculation is produced, because the gas injection rate or the flow rate is very, very large. Now, let me give you an expression of this potential energy, and then we will try to compare both the values by putting some magnitude of free stream velocity, mass flow rate, etc. Now, we know that the buoyancy force, by definition, the system is buoyancy driven, and the buoyancy force, because of the presence of the gas bubble, by definition, mass of displaced fluid multiplied by acceleration due to gravity, and this force is acting along the vertical direction. So, that is what is implied by this particular equation. So, which I can say is equal to rho liquid into volume of displaced fluid. What displaces the fluid? I have a bubble. So, if in a small little volume element, if you imagine the presence of a bubble, so the bubble will displace some fluid, and the buoyancy due to the presence of the bubble is equivalent to the mass of the displaced fluid multiplied by acceleration due to gravity. And I can now say, by using continuity, that this is equal to volume of displaced gas. So, whatever is the volume of the bubble or gas in that particular control volume. So, volume of displaced fluid is exactly equal to volume of bubble gas. This equality is termed as a principle of volume continuity. So, therefore, now the volume of gas, how we can calculate? Let us see, the volume of gas is equal to the volumetric flow rate of gas multiplied by the residence time of gas. How long the gas spends within the plume. And if you do that and say that, well, let this height be is equal to L, capital L, which we call as a depth of liquid. In that case, I would say this is equal to L divided by U sub P, in which I can say that U sub P represents the rise velocity. I am going to talk about it in greater detail later on. So, U sub P essentially represents the rise velocity of the gas liquid plume or the gas liquid mixture. So, L divided by U P represents the time for which the bubbles spend within this system, and multiplied by the volumetric flow rate gives us the volume of gas. This is meter cube per second. This is L divided by U P is equal to seconds. Seconds cancels out. So, this quantity is equivalent to meter cube, and therefore, this is equal to the volume of the gas. Now, if we substitute this here, then what we get? So, therefore, buoyancy force comes out to be rho liquid, then the volume of gas is equal to Q into L by U P. This is the term within the bracket represents the volume of the glass itself. Now, if I say that I want to now find out the rate of potential energy, input due to the bubbles, in that case what I am going to do. So, the bubbles are rising with a certain velocity. Okay. So, if I multiply this with a velocity, I am going to get rate of energy input. If I multiply with a displacement, I am going to get the work done. But on the other hand, if I multiply this with the rate of change of displacement, which is nothing but velocity, in that case I will get the rate of energy input, and this is then going to be equal to rho liquid multiplied by Q L by U P. And with what velocity the gases are rising? As I have assumed here, the gases are rising with a velocity is equal to U P. So, I multiply this U P, and therefore, I get this U P cancels out. This gives me rho liquid G Q into L. So, the potential energy input rate to the gas start system is the density of the liquid multiplied by the acceleration gravity. This is the gas flow rate multiplied by the depth of liquid. Before I proceed further, I wish to now clarify about the gas flow rate. Now, we have injected the gas into the system at suppose some normal meter cube. But the gas, as it enters the system, it undergoes thermal expansion, and also the gas will be injected at certain pressure. It is normal meter cube. So, we have a normal pressure NTP, normal temperature and pressure, but as soon as it enters here, the bubble is subjected to a very high ferrostatic head, 1 atmosphere plus the ferrostatic pressure because of this much height of liquid, which is L. And so, therefore, as the bubble rises, its temperature or the gas develops into bubble, the temperature of the gas gradually increases from its injected temperature, and also its pressure gradually gets decreased as it advances towards the free surface itself. So, the gas temperature here could be 600 degrees centigrade. The moment the gas temperature leaves here could be about 1200 to 1300 degrees centigrade. On the other hand, here the ferrostatic pressure, total pressure, atmospheric plus ferrostatic pressure is very high, and as the bubble rises through the liquid, the ferrostatic pressure afforded by the bubble gradually decreases. So, as the bubble rises, therefore, we can anticipate that because of the temperature increase, the bubble's volume is going to increase, and also because of the pressure increase, also the bubbles decrease, because decrease in the pressure, the bubble's volume is going to increase. So, this pressure temperature effect are actually going to govern the net volume of the bubble. This is not the volume. Suppose if I introduce a bubble which has a volume of suppose hypothetically saying 1 normal meter cube at this particular point, as it is advancing or rising through the molten steel, its volume is not going to be on 1 normal meter cube. Okay, its volume is going to be bigger than that because of the combined effect of pressure and temperature. So therefore, in this analysis, the gas flow rate that we use is referenced to some mean features of this system. Now we say that, well, whatever gas flow rate we are going to use is actually Q in terms of normal meter cube, okay, per minute, say, and then multiplied by and then we say it is equal to 1 atmospheric pressure. So P is equal to 1 and this is equal to P plus P1 plus rho GL into. I have taken L by 2 to state specifically that the pressure, reference pressure, because volume is not defined unless I categorically mention the pressure and the temperature. And I am saying that, well, the gas in this system immediately attains the mean bath temperature, which is 1873 degrees centigrade, and this T is the normal temperature. So this is actually equal to 298, 273 plus 25 degrees centigrade. Normal temperature and pressure, so it is 1 atmospheric pressure, okay, and this is going to be pressure. Sorry, this is going to be actually other way around. This is P plus 1 rho liquid GL by 2, because the volume is going to be inversely. So this is the pressure we are talking about at the mid bath radius position, and this is the pressure is the corresponding to the normal pressure, which is about 1 atmosphere. So this term is equal to 1 atmosphere plus the corresponding atmospheric pressure translated in terms of the mid bath depth, which is nothing but. So the gas flow rate that I am using in this particular formula is, therefore I will say, with respect to, or it is converted to the mean temperature and pressure of the liquid. Mean temperature means it is the 1600 degree bath temperature. Mean pressure means the total pressure at this particular point, which is equal to 1 atmospheric pressure plus rho g L by 2. So if I use a corrected gas volumetric flow rate, which is reference to the mean temperature and mean pressure of the liquid, I am going to really experience the net potential energy which is supplied. If I work out the potential energy supplied on the basis of normal meter cube, it is going to be considerably under predicted, because my analysis would not have taken into account the expansion of the gas volume because of the reduction in pressure as well as increase in temperature itself. So it is a very important point to note at this particular point, that the flow rate, volumetric flow rate that is used in this formula is actually a gas flow rate which is corrected to mean height and temperature of the liquid. Now if we substitute the values, for example, in industrial system, rho liquid is 7000 kg per meter cube, G is equal to 9.81, Q, this factor will come out to be 5 to 6 times. Multiplication factor is going to come out here, and then we see that if we use 1 normal meter cube of flow rate per minute, this could be about 5 to 6 normal meter cube. L, or the depth of the liquid in industrial system, is about 3 meter, and if we substitute these values together with the potential energy values, we can immediately show that indeed the kinetic energy supplied by the gas, injected gas, is barely 1% of the potential energy afforded by the rising bubbles to rise through the system itself. So it is basically, one can carry out simple expression, and one can on the basis of this show that it is a potential energy driven system. Now the buoyancy force per unit volume, I can also deduce buoyancy force per unit volume. Per unit volume means per unit volume of the plume. So I have rho liquid, this is, I have volume of gas, and multiplied by acceleration due to gravity divided by volume of plume, and this in which alpha average represents the average gas fraction in fact, we have some very high gas concentration at this particular point, maybe 80%, 90%. On the other hand, we have dispersed bubbles here, the gas volume fraction, because the plume expands. So we have the gas volume fraction continuously decreasing as the plume would expand towards the surface itself. So there is a variation of gas volume fraction within the system, but we would say that we can average it out over the entire volume, and this alpha average, whatever I have shown towards the right, is actually the mean gas volume fraction of in the plume. Now, this mean gas volume fraction in the plume, therefore, by definition is equal to alpha average is equal to volume of plume, volume of gas and volume of plume. Now, volume of gas, I have already given you the expression, and if I assume that, well, this plume is roughly conical in shape, okay, in that case I can say this is going to be is equal to 1 by 3 pi r e square L. What is r e square? Then r e square is exactly equal to the radius of the plume I. Okay, and if I take the value of the volume of the plume as this 1/3 pi r e square L, calculate the volume of the gas on the basis of this formula, I will find out that the average gas volume fraction here is barely 5%. So it is a very important deduction and a very important point for us to remember that the gas volume fraction within the two phase region is actually very, very small quantity. 5% of this region is occupied by argon bubbles and remaining. So given this picture, we can now conceptualize the gas injection phenomena, that it is like an unconfined jet, okay, because the gas volume fraction is very, very small. It is rising through a very deep bath. The bubbles are not going to see the walls. They are not, they are located far away. So as if it is, an unconfined liquid stream of bubbles which are rising through, or a buoyant plume which is rising through, and the energy is transferred to the molten steel bath across the boundaries itself. So all along this, because of the buoyancy itself, energy is going to be continuously transferred. The bubbles are going to give rise to their energy, give away their energy to the fluid. While they leave the system, the fluid will keep on recirculating, thereby generating a strong convection current in the system itself. So I have introduced a term which is the plume velocity. This plume velocity essentially implies the rise velocity of the gas liquid mixture. I have gas plus liquid here. So the average rise velocity of the gas liquid mixture. In fact, I have bubbles which rise there with certain velocity, and I have the liquid within the plume which rises with some velocity. So I actually have a bubble rise velocity, bubble rise with their velocity, bubble rise velocity, and I also have liquid rise velocity. Typically, the bubbles rise faster, and the difference between the rise velocity of bubble and liquid is termed as the slip velocity. So the bubbles accelerate faster, rises faster, the liquid follows it, and together we can conceptualize of an average velocity of the gas liquid mixture, which we term as an average, call it a plume rise velocity. There is another important parameter which is like we denote by mean speed of liquid recirculation, mean speed in the system, mean speed of liquid recirculation. Which represents like the average velocity in the system. Now, for example, I have an object where I can have, say, I divide it into 4 segments. Here there is 100 degree centigrade temperature, 200 degree centigrade temperature, 300 degree, and I say that, well, there is a difference in temperature, but nevertheless I can ascribe a average. In this case, if all the control volumes are identical, it is 4 plus 3 plus 2 plus 1. So 1000 degree divided by 4, which is equal to 250 degree, will be the average temperature. Similarly, even though we may have different velocities here, we can ascribe a constant or a mean velocity to the system, and this is termed as denoted by u bar, okay, and this is called the mean speed of liquid circulation. Why we are talking of velocity scales all on a sudden here is that it is important for us to know the scale of velocity in the system, because we would like to do some calculations regarding alloy dissolution, alloy mixing, slag eye area, etc. And as I have mentioned, inclusion flotation as well, and as I have mentioned that steel making systems are basically mass transfer control systems. So therefore, the convection current is going to assume predominance in such processes. So mixing, mass transport, alloy dissolution, temperature distribution, convective heat and mass transport, everything is going to be a function of the velocity, and that is why we have to have some idea of the velocity scale in the system, and then only we can conclude whether the Argonstadt system is really efficient or not in terms of its processing capabilities. There are basically many equations people have derived. This is of course not within the purview of this course, but simple macroscopic equations which is available in the literature. For example, the plume rise velocity is given in terms of by 3, and similarly this is in SI unit, and mean speed of liquid recirculation, for example, is given also Q raised to the power 1 by 3, L raised to the power 1 by 4, and R raised to the power minus 0.8. Let us concentrate on UP. So this is a constant which comes out from various parameters, like what is the bubble diameter, what is the bubble rise velocity, what are the properties of the system, and so on. Q represents the gas flow rate, and as I have been mentioning all the time, this is the gas flow rate corrected to mean height and temperature of the liquid. L represents the depth of liquid, which is basically this, and R represents. As the formula suggests, that the plume rise velocity, or the average velocity, rise velocity of the bubble and the liquid mixture, will increase as third power of the gas flow rate. It will increase also relatively weakly as depth of liquid, but it is going to decrease with the vessel radius. So therefore, for a given flow rate and given liquid depth, the more is the diameter of the vessel, the less is going to be the convection current or the plume rise velocity in the system. And same sort of a functional relationship one can see here, that both average velocity and liquid plume rise velocity are offset by any increase of the vessel radius. On the other hand, by increasing the gas flow rate and liquid depth, we can increase the rise velocity as well as the mean speed of path recirculation. Now, typically these are under the ladle metallurgy steel making conditions. These correlations cannot be really applied to a very large flow rate situation in which the gas injection rates are very, very large, or the bath is extremely shallow or extremely tall vessel. So these are not the conditions. Under typical ladle metallurgy condition, only these equations hold good. Now, therefore, a taller vessel is going to give rise to more convection current. Now imagine we have said that potential energy input rate, which is typically denoted by epsilon dot, is equal to rho liquid G Q into L, and this tells us that, look, if we increase the gas volumetric flow rate, or if you increase the depth of liquid for any given system where rho L is constant, the rate of energy supply is going to be increasing. Okay, and it is because of that more energy means more rate of recirculation, and that is being reflected in this particular formulae as well. There is another term which is also important for us, which we will use, is the energy input rate per unit mass. So this is energy input rate, and this is energy input rate per unit input rate per unit mass. and this is denoted typically GQ by pi r square, in which the ladle has been assumed to be perfectly cylindrical. So, the volume is basically pi r square, and therefore, rho L into pi r square L. So, rho L is going to cancel out, L and L is going to cancel out. So, GQ will remain in the numerator, and in the denominator we have pi r square, and this value under little metal at the steel making condition is basically of the order of 0.1 watt per kg. That is the rate of specific potential energy input rate to the system. Now, for the same amount of specific potential energy input rate, on the basis of this equation, I can show that, well, there will be more higher plume rise velocity in system if they are taller, and there will be more recirculation if the system is going to be bigger capacity. So, using this formulae as well as these prescriptions, I can very well show, that is for you to do this calculation. And so, at the same specific gas flow rate, or energy input rate, same energy input rate, taller vessel is better, higher capacity vessel is better. Better means, in higher capacity vessel, the efficiency of stirring is going to be more intense stirring for the same amount of specific gas flow rate or same specific potential energy input rate. A taller vessel is also going to be better. So, if you say that depth of liquid is higher, that means the stirring is also going to be higher at the same volumetric, specific volumetric flow rate or same potential energy input rate. So, this one can very easily show. So, I can say that a 500 ton ladle is going to be far more effective than a 200 ton ladle, for example, at the same specific gas flow rate. Also, I can say that a vessel which is 2.5 meter depth is going to be more effective than a vessel which is only 1.5 meter depth at the same value of specific potential energy input rate. Let us now examine the issue of gas liquid interactions in the ladle. Typically, because argon is injected, so we would say that there is no chemical interaction, because the solubility of argon in steel is negligible, no chemical interaction. So, whatever interaction is possible in the system is basically thermal interaction. So, this is significant for us, thermal interaction. Now, there might be some misconception at this particular stage, saying that, well, an argon is introduced into the system at 298, and if it leaves the system at close to 1400 or 1300 degree centigrade, okay, or 1673 Kelvin, it might appear that lot of heat is being taken out by the gas, because the gas is going to consume lot of heat from the metal, and as a result of which can give some kind of a chilling effect on the metal itself. But simple calculation can show that the rate of temperature drop of the melt because of this rise in gas temperature is really not significant. For example, okay, if I write down the balance, that heat taken up by gas is equal to heat lost by melt. This is a thermal balance equation under steady state condition, and if I now take that, well, delta T is equal to, say I have injected it, so it is about 1673 minus 298, so roughly about 1375. Kelvin. If I say that my gas flow rate is something like say 1 nm cube, per minute per ton. In that case, I would say, let me just do this, 1 normal meter, 40 normal meter cube per 40 normal meter cube. This is a typical arcing flow rate, and then we can do the calculation that for this much of temperature, we know the specific heat of gas, Cp gas, and we know Cp liquid molten steel. These values are known to us, and we can plug in these values for this energy balance equation, and then show that, well, for this kind of a temperature rise in gas temperature is going to introduce a delta T in liquid, which is approximately is equal to, or I can say less than equal to, an insignificant drop in temperature. Simple calculation mCp dt I can do and write down the balance equation using the data. The gas specific heat can be obtained. The liquid specific heat also is known to us, which is about, I think, 632 joules per kg per Kelvin. This is a value of, I think, 0.5, if I remember correctly. And if I substitute the value, I should be able to find out that because of this much. And why is this difference occurring? The difference is occurring because of the density of liquid is significantly smaller than the density of the gas. While it is 7000 kg per meter cube, this is barely 0.1 or 0.2, and therefore this large difference actually does not cause a noticeable extent of temperature drop. So the gas, even though it is going to be heated up to 1400 degrees centigrade, it is really not going to take much heat from the melt itself. In fact, the heat loss through the free surfaces, I can say Q, this is a standard notation. So all this through all these surfaces, heat is going to be lost, and the loss of heat, this loss of heat through the surface of the ladle, free surface, as well as the bounding walls through refractory line walls of the ladle, is going to cause actually noticeable amount of drop in the melt temperature itself. And I think I have given you the value that actually for holding, due to this heat fluxes prevalent through the wall, refractory wall, as well as the slag lined free surface, the drop in temperature of the melt is of the order of 0.5 degrees, which essentially means that if we gas stir a ladle for about 30 minutes, there will be 15 degrees of drop because of loss of heat to the surroundings. On the other hand, in that particular time, we may have 0.3 degree drop because of the heat which is consumed by the rising gas. So therefore, we can conclude that the injected gas, even though it is cold, it is heated up to about 1400 degrees centigrade due to its low density and low flow rate. The loss of heat is from the melt is going to be insignificant in comparison to the loss because of heat going out of the system to the surrounding through the free surface as well as the wall. Now, we can talk about the slag cover in the system. To minimize, so therefore, we have to have some kind of a slag layer here. Otherwise, if this surface is exposed, the drop in temperature could be significantly larger, because this surface is at 1600 degrees centigrade, and you know that the radiation loss is proportional to delta theta raised to the power, I would not say delta theta, I would say theta 1 to the power 4 minus theta 2 proportional to. So theta 2 may be the ambient temperature, theta 1 may be the surface temperature. The radiation heat flux is proportional to the temperature. So the surface temperature, if it is exposed, could be 1873, and therefore you can imagine the extent of radiation heat loss if the surface is not exposed. The slag layer basically does two things. It provides a protective environment that the metal which is refined and quality is good. We have made a lot of effort to produce a good quality steel here and are continuously refining. We would not like this metal to interact with the bulk air, so that reoxidation etc. can take place, and also we want to minimize the drop in temperature, and therefore we have to have some covering of slag at the free surface. And this slag, as I have mentioned to you earlier, is not an oxidizing slag. It does not contain FeO. It contains freshly prepared slag with some lime, silica, etc. and so on. Now, basically the slag cover can be thin or thick. And how thick is this slag cover? This is barely maximum. If you look at 150 ton ladle, 150 ton ladle for example, and the amount of slag is about 4 to 5 tons. This is the slag, and if you convert them into their corresponding height, taking into account the density of steel, which is 7,000 kg per meter cube, and the slag density, which is about approximately 3,000 kg per meter cube, depending on the density, could be 2,340, a typical density. You can translate this into the corresponding height, and you can see that the thickness of the slag typically in industrial process is approximately maximum 1% of the bud depth L. So, the thickness of the slag is very, very small. We would also like, as I said, that some covering. This is an exposed plume eye area, for example, through which we can have lot of interaction with the environment, and it is possible for us to cover up this by increasing the thickness of the slag. If the slag is increased, you can see that the slag eye area, the exposed area, can be really very, very small. So, I can show this by using a colored chalk here. So, this now represents, for example, okay, the exposed area when your slag is really thick. So, by using a thick slag, it is possible for us to cover a portion of the slag eye itself, and thereby minimize the interaction of molten steel with the surrounding atmosphere itself. And when you are talking of thick slag, the thick slag we are talking about, this is thin, and thick slag we are talking about is approximately 5%, and that would tend to cover up. So, thin slag, as I have mentioned, is barely 1% of the entire bath depth. On the other hand, the thick slag is going to be about 4 to 5%, but most of the industrial processes, ladle metallurgy processes, employ a thick slag, thin slag. Now, if I use a thick slag, for example, I can show that it is possible under that condition to really cover up the entire plume eye itself. So, this represents an extremely thick slag, whereby the plume eye can be completely submerged under the slag layer itself. And this height, we basically we say that this is the dome height H sub d, or which is equal to now the delta sub L. So, this is the eye height or the dome height, and this dome height now becomes exactly equal to the thickness of the slag itself. And under such condition, if you look at the figure, the eye is now, the plume is now completely submerged, and there is very little scope for the surrounding atmosphere to interact. No, this is now not possible because the surface is totally covered. So, under that condition, we can see, we can also write that, well, this is the axis, and at this axis what happens? The potential energy, okay, because of the raising, if there is no gas injection, this surface which is raised up by H sub d will immediately fall down, and the entire bath depth will come. So, the potential energy or lifting of this surface by an Hd is exactly equal to, because of the kinetic energy of the plume. So, we can say that half Up square is equal to this is an expression. Energy balance, kinetic energy afforded by the plume is exactly equal to the potential energy because of lifting of the surface by d, and therefore we can say that H sub d is equal to up square. And up expression of up I have already given. Up is equal to 4.4 q raised to the power 1 by 3, L raised to the power 1 by 4, and R raised to the power minus 1 by 3. So, given the gas velocity, given the gas flow rate, we can convert it into the actual condition, which is reference to our mean height and temperature of the liquid. We can use the depth of liquid in the system, radius of the vessel, calculate the plume velocity in SI unit, substitute it here, and then calculate that what is the dome height, and then set it to be equal to delta L, and find out that what should be the thickness of the protective slag layer, which can really cover up the entire dome, thereby minimizing the chances of interaction between the melt and the upper ambient atmosphere. Now, this slag eye is a very important aspect of secondary steel making operation. We are gradually closing down now on various aspects of inert gas injection. The slag eye area, for example, is a potential site of reoxidation, okay, and particularly towards the final stages of little rinsing operation or argon starting operation, we want to homogenize the bath, mix the bath. I am going to talk about mixing, which is very important in the context of ladle metallurgy within the next few minutes. So, during the final stage of ladle metallurgy operations, when we are injecting the gas at a very slow rate, 0.1 normal meter cube per minute per ton, and at that condition we will really like to see that there is not much interaction with the atmospheric oxygen. We have to prevent the reoxidation, which is the culprit for aluminum fading and formation of more oxide inclusions in the bath. So, therefore, to minimize that, we will have to have the process should be regulated in such a way that eye area remains very, very small. Now, the exposed eye area, area of the plume, area of the eye to area of the plume is equal to, roughly is equal to, we have a constant alpha, beta, then we have up square by g delta L raised to the power 0.5, and then we have rho L divided by delta rho. The density differential and the plume rise velocity gives us, determines the ratio of the eye to the ratio of the plume, because you can always see that sometimes you can see that the slag is here, okay, the slag, for example, is here and the plume is somewhere. The slag is pushed to such an extent that actually this is the eye area that we are talking about, and this is the area of the plume that we are using in this particular formula. So, there are two areas here, and this tells us that the eye is actually and AP. So, because the flowing liquid, radially flowing liquid, the liquid goes like this, it comes like this. So, it has been able to push this slag layer, this is the slag layer, it puts this slag layer, and as a result of which we are creating a bigger opening than actually the area exposed. So, therefore, we can say that the eye area is bigger than the plume area under that particular condition, and we can have an equation like this, which tells us that the thickness of the slag layer, the plume rise velocity, and the density of the slag are critical parameter in determining that how much of area is going to be really exposed, and thereby we can say that whether there is going to be significant amount of reoxidation or not in the system. One of the objectives of inert gas stirring is to enhance mixing in the system. As I have mentioned that we would like to induce velocity all the time, we want to transport a species from one position to another position and facilitate reaction between the various species. We can also think of transporting the product, moving the product from the reaction sites, and all these are going to be aided by a strong convection current which is going to be prevalent in the system. We also may have different temperatures at different regions, and we may do gas stirring. Obviously, for example, as I have said, if there is more heat loss to the surface, the temperature here is going to be cooler than the temperature here, temperature at the center, temperature here is going to be cooler than the temperature here, and so as a result we may have some thermal stratification in the system, and we can remove that thermal stratification by gas stirring, so which does some amount of thermal mixing. Similarly, we can say we may have some inclusion differential counts in the system, and we can have gas stirring, and the gas stirring is going to give rise to some uniform inclusion distribution in the system. So, material mixing and thermal mixing are important objectives of gas stirring, and when we talk of mixing, we must understand that mixing are basically macro mixing and micro mixing. In engineering, we always talk about macro mixing, not micro mixing. Micro mixing means mixing at the molecular level, but in engineering applications we are not really concerned with micro mixing, we are concerned about macro mixing. What are the mechanisms of mixing? The mixing is aided, macro mixing is basically due to flow and turbulence. I must mention at this particular stage that the flow which is induced in the system, even though the flow rate may be small, gas injection rate may be small, even though the velocity, scale of velocity may not be significantly high, but the flow which is induced in gas stirred Ladle system is highly turbulent. Based on what I make this supposition? If I calculate on the basis of, say, a Reynolds number in the system, then the Reynolds number can say how it is defined. It is defined in terms of the kinematic viscosity in the denominator, and then we have characteristic velocity if I take that to be is equal to up, and then a characteristic length scale if I take that to be the depth of the liquid. Now, if I calculate this, substituting the values of a relevant industrial size ladles, for example, the kinematic viscosity in SI unit is of the order of steel is of the order of 10 to the power minus 6 meter square per second. This depth of liquid typically about 3 meters, and under ladle metallurgy steel making conditions in steel processing ladles, the value of up is of the order of 1 meter per second or so. So, if you substitute these values, then I am going to get a Reynolds number, a dimensionless number, and that number is going to give me the ratio of the inertial to viscous forces, and this is going to come out to be much larger than 10 to the power 5. This is the velocity that is on the basis that is due to the potential energy supplied to the system, and I should not calculate the Reynolds number based on the orifice velocity, because the orifice velocity is insignificant as far as the stirring in the system is concerned. A more representative velocity is up. Similarly, I should not calculate Reynolds number based on the diameter, because the energy input to the system is governed by the depth of liquid in the system. So, on the basis of this, I can therefore say that the viscous force is 10 raised to the power 6 times smaller than the inertial force, and a high Reynolds number 10 raised to the power 5 times smaller than the inertial forces. So, therefore, I can say that since the Reynolds number is going to be greater than 10 raised to the power 5, we can conclude that the system is inherently turbulent. Okay. So, the large size of the steel processing vessel, the smaller kinematic viscosity of steel precludes roll Reynolds number or laminar flows. So, therefore, it is an important understanding at this stage that in most of the steel making vessels, the fluid flow or molten steel motion that we are going to see, that are going to be basically turbulence, and as we know that turbulence aids in heat and mass transfer. Okay. If there is more turbulence, means fluids can jump from one point to another point, and along with them they can take heat, they can take mass, and therefore aid in more mass transport and heat transport, and therefore macro mixing in industrial ladle system is because of the flow, which is we are talking about the mean flow or the convection current that we see, and also on top of that turbulence plays a major role as far as mixing is concerned. Now, just like the way I have given you an equation, I come back to this equation and I would like to mention that these are constants, for example, and these constants are not yet determined specifically for industrial systems, because it is so difficult to make realistic measurements of eye area and plume area in industrial system itself, but we do carry out some modeling studies in laboratory, and based on laboratory, some laboratory scale work, particularly cold model work, we have some values of alpha and beta, but for actual industrial system, the exact values of alpha and beta at this stage are not known with any certainty. So, similarly, based on models also, we have derived equations for mixing, and the mixing time is typically for an axisymmetric gas stirred ladle system, for example. Now, you see the exponent on L and R changes drastically. For example, plume rise velocity, as the velocity would increase, the mixing time is going to go down. Time, this is the mixing time, time to attain a given degree of homogeneity. So, if efficiency of mixing is very high, I can say that mixing time is small. If efficiency of mixing is very small, I can say that the mixing time is going to be larger. So, the time to reach a certain degree of homogeneity, how much mixed? 99% of it is mixed or 95% of it is mixed. So, I can say that 95% mixing time or 99% mixing time, it is a constant, and this equation is again in SI unit is q raised to the power minus 1 by 3. So, an increase in gas flow rate will increase in velocity, but decrease in mixing time, because as the intensity of flow increases, the efficiency of mixing increases, and as a result of which mixing time goes down. Similarly, if vessel is more tall, the dip is liquid is very deep, in that case there is going to be more energy input rate. So, there is going to be more stirring, so as a result of which I can expect that the intensity of mixing is going to be large, and as a consequence I would say that the mixing time is going to be shorter. And similarly, when the velocities are proportional to r raised to the power minus 2, minus 2.3, etc., in this case you see that the exponent on r is positive, which essentially tells that a bigger diameter vessel, okay, for a certain flow rate q and certain liquid depth L is not conducive for shortening mixing or enhancing the efficiency of mixing. Now, this correlation which I have shown here is an empirical correlation, and it is found to be valid for axisymmetric gas stirred. So, there is a single plug located at the center of the vessel, and for that particular case with negligible amount of slag, there is no slag layer here. You see, I do not have any parameter like this. So, I would say in the absence of any slag, this is the correlation which people have found to work. Again, I repeat that this sort of a correlations are really derived from model studies, because it is so difficult to carry out high temperature experimental observations in steel making operation.